Hello, everybody. I'm so happy that you're here with me today. Today, I would like to read with you the paper MusicLM, Generating Music from Text. Oh boy, this is going to be gorgeous, generating music from text. After all these months, generating pictures from text, prompt engineering, stable diffusion, Midjourney, DALL-E 2, you name it. Well, we are all very, very interested in the idea, can this be applied to other domains as well? Here's a fine paper. January 26th, 2023, so still rather young, at least in my calendar. We still are in February. And, well, what I already know comes from Google. Very interesting to say the least. Let's have a look. First, the abstract. We introduce MusicML, a model for generating high-fidelity music. Already very interesting. High fidelity means lots and lots of frequencies and high quality. Music from a text description such as a calming violin melody backed by distorted guitar riff. Well, this is what everyone would like to have. You have a piece of text, and automatically from this text you can generate a piece of music. MusicLM casts the process of conditional music generation as a hierarchical sequence-to-sequence modeling task. Sequence-to-sequence modeling task, and is hierarchical. And it generates music at 24 kilohertz. That's okay. That remains consistent over several minutes. Well, it's even better, consistent over several minutes. Our experiments show that MusicLM outperforms previous systems, both in audio quality and adherence to text descriptions. That's good. Higher audio quality and higher adherence to text descriptions. Moreover, we demonstrate that MusicLM can be conditioned on both text and a melody, in that it can transform whistled and hummed melodies according to the style described by it in a text caption. This is cool. Conditioned on both text and the melody. So the idea is you provide a text and you provide a melody, here by humming as an example, and it generates some music for you. To support future research, we publicly release MusicCaps, a dataset compared of 5.5K music text pairs. This is cool. You always need that. MusicCaps dataset of 5,500 music text pairs with rich text descriptions provided by human experts. Well, that's the trouble. We always face that we don't have enough data. Well, we have enough music data to train on, don't get me wrong. But labeled data, that's always the bottleneck. And 5,500 music text pairs is, well, not that much, to be honest, but I think it's just the beginning. Let's see, introduction. Conditional neural audio generation covers a wide range of applications ranging from text to speech. Okay, that's what we already know. I mean, it's all the story in the book that you have a text and you map it to a speech synthesis. Lyrics, conditional music generation, and audio synthesis from MIDI sequences. So remember that the Magenta people are currently working on end-to-end, from MIDI to audio in just one neural network. Such tasks are facilitated by a certain level of temporal alignment between the conditioning signal and the corresponding audio output. That's very important. Input and output. Temporal alignment means that, for example, when you have lyrics and you create a singing voice, so that it's aligned in rhythm. In contrast, and inspired by progress in text-to-image generation, recent work has explored generating audio from sequence-wide high-level captions, such as whistling with wind blowing. While generating audio from such coarse captions represents a breakthrough, these models remain limited to simple acoustic scenes consisting of few acoustic events over a period of seconds. Hence, turning a single text caption into a rich audio sequence with long-term structure and many stems, such as a music clip, remains a challenge. So this is where we currently are. Generating tiny little sequences is not a big problem, but having rich and longer sequences, that's the problem. AudioLM has recently been proposed as a framework for audio generation, casting audio synthesis as a language modeling task. The plot thickens. Casting audio synthesis as a language modeling task in a discrete representation space. So what's behind that is, I would guess, using transformers on, well, here we are, as tokens, so using transformers. Transformers work with tokens. The problem is that music is continuous, but there seem to be ways how to map the continuous pieces of music to discrete tokens. MusicLM achieves both high fidelity and long-term coherence over dozens of seconds. Moreover, by making no assumptions about the content of the audio signal, MusicLM learns to generate realistic audio from audio-only corpora, be it speech or piano music. So this is definitely something to also have a look at, MusicLM, because it seems to apply on quite a lot of data, or can say different kinds of data without any annotation, self-supervised training. The ability to model diverse signals suggests that such a system could generate richer outputs if trained on the appropriate data. Also cool. So there's a certain hope. That's where I think the authors would continue. Besides the inherent difficulty of synthesizing high quality and coherent audio, another impeding factor is the scarcity of paired audio text data. Yeah, this is horrible. The scarcity of paired audio text data, already mentioned this. You can only get a high quality generation or high variability generation if you have enough data to train on. This is in stark contrast with the image domain. Well, I mean, we're talking in the image domain about millions and more than millions of samples that we can train on, where the ability of massive datasets contributed significantly to the remarkable image generation quality that has recently been achieved. Stable diffusion, DALI, and so on and so forth. Moreover, creating text descriptions of general audio is considerably harder than describing images. Well, preaching to a choir here. Talking about music, I mean, hopefully you did this exercise, describe a piece of music to someone else. Only describing taste, wine tasting is worse. First, it is not straightforward to unambiguously capture with just a few words the salient characteristics of either acoustic scenes or music. Second, audio is structured along a temporal dimension, which makes sequence-wide captions a much weaker level of annotation than an image caption. So that's a crucial part. If you have a long piece of music, then any description that applies to the beginning might not apply to the end. In this work, we introduce MusicLM, a model for generating high-fidelity music from text descriptions. MusicLM leverages AudioLM's multi-stage autoregressive modeling. Interesting. Multi-stage autoregressive modeling as a generative component means predicting the next token while extending it to incorporate text conditioning. Adding, I would say, or at least I would expect, another input. To address the main challenge of paired data scarcity, we rely on MULAN, a joint music text model that is trained to project music and its corresponding text description to representations close to each other in an embedding space. That's cool. So you have a latent space somewhere, and this latent space contains both text descriptions and music representations, and they are close to each other in latent space. That's cool. This shared embedding space eliminates the need for captions at training time altogether, which allows training on massive audio-only corpora. Yeah, this is cool. Massive audio-only. That is, we use the MULAN embeddings computed from the audio as conditioning during training, while we use MULAN embeddings computed from the text input inference. When we trained on a large dataset of unlabeled music, MusicLM learns to generate long and coherent music at 24 kHz for text descriptions of significant complexity, such as, another example, enchanting jazz songs with a memorable saxophone solo and a solo singer, or early 90s techno with low bass and strong kick. To address the lack of evaluation data for this task, we introduce music caps. Another thing. Lack of evaluation data for the task. It's always difficult to come up with some objective measure for generated artifacts, especially in music. We introduce music caps, a new high-fidelity music caption dataset with 55K examples prepared by expert musicians, which we publicly release to support further research, which is very good. There's another dataset available. Makes me very, very happy. Our experiment shows through quantitative metrics and human evaluations that MusicLM outperforms the previous systems such as MuBERT and Refusion, both in terms of quality and adherence to caption. It's typical for a paper that you put the contributions in relationship to previous work and hopefully you outperform it. Furthermore, since describing some aspects of music with words can be difficult or even impossible, we show how our method supports conditioning signals beyond text. Concretely, we extend MusicLM to accept an additional melody in form of audio. Whistling and humming as conditioning to generate music. I mean, how cool is that? Imagine that you have a tool where you just whistle something and it generates a piece of audio, a piece of music from that. Is just cool. I mean, it opens a completely new door to human-machine interaction. Well, and as you might know, interacting with computers in order to create music, is very bottleneckly, to say the least. We acknowledge the risk associated with music generation, in particular, the potential misappropriation of creative content. Copyright issues. In accordance with responsible model development practices, we conduct a thorough study of memorization by adapting and extending the methodology of Carlini et al. I think this is how much the approaches memorize the original data used for text-based large language models. Our findings show that when feeding Moulin embeddings into MusicLM, the sequence of generated tokens significantly differ from the corresponding sequences in the training set. Okay, again, something that we learned from this. There seems to be some research on novelty. You would like to have a neural network that generates new data and not data just by pure copying from the original data set. And they applied it from language models, text models, natural language processing to music. The key contributions of this work are the following. We introduced MusicLM, a generative model that produces high-quality music at 24 kilohertz, which is consistent over several minutes while being faithful to text conditioning signal. Cool. We extend our method to other conditioning signals, such as melody, that is then synthesized according to the text prompt. Furthermore, we demonstrate long and coherent music generation up to 5-minute long clips. 5 minutes, quite a lot. We know that pop music is never that long. We released the first evaluation dataset collected specifically for the task of text-to-music generation. MusicCaps is a hand-curated high-quality dataset of 5.5 music text pairs prepared by musicians. Awesome. So that's where we currently are. There seems to be an improved approach, high-quality audio, which can be also conditioned on other signals, and of course, there's an evaluation dataset. Makes me quite nervous in a good way. Background and related work. The state-of-the-art in generative modeling for various domains is largely dominated either by transformer-based autoregressive models, predicting the next token, here's again, attention is all you need, or U-Net-based diffusion models. That's where we currently are, diffusers. In this section, we review the related work with an emphasis on autoregressive generative models operating on discrete tokens, which share similarities with MusicLM. So this is really, really impressive, because it tells you it's attention-based models. At least I would expect attention-based models here. Quantization. Now comes the crucial part. When we remember, I think I said it already, audio data, including music data, is usually discrete data. So you have time series with different frequencies over time. And the problem with that is, well, no, this is not a problem, but when we think about the other domains, natural language processing, we always talk about tokens, and tokens are discrete tokens. It means there is no spectrum of meaning. There's like every word has a certain representation. Usually there are pieces or elements of a vocabulary. And the problem is, well, music is continuous. Transformers and other autoregressive models want to have discrete data as tokens. How can you map music and audio to tokens? This is called quantization. Modeling sequences of discrete tokens autoregressively has proven to be a powerful approach in natural language processing. Well, I think those papers might be the GPT papers. GPT-3, for example, is an autoregressive model. like GPT-2 and GPT-1 and ChatGPT and all the other transformers that we talk about, most of the other transformers we talk about. Codecs is another example. And images or video generation. Quantization is a key component to success of autoregressive models for continuous signals. There you go, time series, including images, videos, and audio. The goal of quantization is to provide a compact, discrete representation, which at the same time allows for high fidelity reconstruction. So see, it's both directions. You would like to take a piece of, for example, audio, map it to a or multiple discrete tokens, and from any discrete token sequence, you would like to reconstruct the audio. VQ VAEs demonstrated impressive reconstruction quality at low bit rates in various domains and serve as the underlying quantizer for many approaches. So VQ VAE is one way to do this. Soundstream is a universal neural audio codec. Cool. Capable of compressing general audio at low bit rates while maintaining a high reconstruction quality. Okay, seems to be another approach. To achieve this, Soundstream uses residual vector quantization, something to also have a look at, allowing scalability to higher bitrate and quality without a significant computational cost. Okay, this means that embedding or encoding and decoding might be quite fast. More specifically, RVQ is a hierarchical quantization scheme composing a series of vector quantizers where the target signal is reconstructed as the sum of quantizer outputs. Due to the composition of quantizers, RVQ avoids the exponential blow-up in the codebook size as the target bitrate increases. Codebook size, I think this means how long the codes are that you generate from the audio. Moreover, the fact that each quantizer is fitted to the residual of coarser quantizers introduces a hierarchical structure to the quantizers, where coarser levels are more important for high fidelity reconstruction. This property is desirable for generation since the past context can be defined only by attending to the coarse tokens. Recently, Soundstream was extended by encodec. Aha, so there's a third player in the room now. By encodec to higher bit rates and stereophonic audio. So stereo, two channels, right and left, left and right. In this work, we rely on Soundstream as our audio tokenizer, since it can reconstruct 24 kilohertz music at 6 kilobits per second with high fidelity. So it's Soundstream. Soundstream makes it, this one, not the other two. This is going to be our encoder for data, our tokenizer. Next, generative models for audio. Despite the challenge of generating high-quality audio with long-term consistency, so over a long time we still have consistent music generated, a series of approaches have recently tackled the problem with some success. Jukebox, just by OpenAI, for example, proposes a hierarchy of VQVAEs at various time resolutions to achieve high temporal coherence, but the generated music displays noticeable artifacts. Okay, while Jukebox is a little older, it also uses transformers for predicting the tokens, and then comes the reconstruction part. I tried it out in the past. I was not really convinced, but it's a couple of years ago. On the other hand, proposes to model a sequence of Soundstream tokens, autoregressively achieving high-quality audio, but compromising the long-term temporal coherence. Okay, so here, the perceiver AR is another approach where you work with Soundstream tokens, achieving high-quality audio, but compromising the long-term temporal sequence. Better audio, worse coherence. Inspired by these approaches, MusicLM addresses the trade-off between coherence and high-quality synthesis by relying on a hierarchical tokenization and generation scheme. Concretely, the approach distinguishes between two token types: semantic tokens, that allow the modeling of long-term structure extracted from models pre-trained on audio data with the objective of masked language modeling. Masked language modeling sounds like bad to me. And second, acoustic tokens provided by a neural audio codec for capturing fine acoustic details. This allows MusicLM to generate coherent and high-quality speech as well as piano music continuations without relying on transcripts or symbolic music representations, which is cool. So you don't need any text and you don't need any sheet music in order to generate audio from this. Okay, so we have semantic tokens on one side for the long-term structure, and you have acoustic tokens for, I'll say, acoustic details. MusicLM builds on top of AudioLM with three important additional contributions. First, we condition the generation process on a descriptive text. So there's another signal, another input signal, a text description. We show that the conditioning can be extended to other signals such as melody, heard that, and three, we model a large variety of long music sequences beyond piano music, from drum and bass over jazz to classical music. Gets me even more excited. Next, conditioned audio generation. Generating audio from a text description, such as whistling with laughter in the background. I love all those examples that are here, that are sprinkled on top of this paper. Has recently been tackled by several works. Diff Sound uses CLIP as a text encoder and applies a diffusion model to predict the quantized Mel spectrogram features of a target audio based on the text embeddings. AudioGen uses a T5 encoder for embedding the text and an autoregressive transformer decoder for predicting target audio codes produced by encodec. T5, cool. That comes from the original transformer encoder-decoder architecture. Both approaches rely on a modest amount of paired training data, such as audio set and audio caps, so two data sets, totaling less than 5,000 hours after filtering. Well, 5,000 hours. It's quite something if you want to listen to it. Closer to MusicLM, there are also works focusing on music generation conditioned on text. In MuBird, the text prompt is embedded by a transformer. Music tags, which are close to the encoded prompt, are selected and used to query the song generation API. Based on the selected tags, MuBird generates a combination of sounds, which in turn were generated by musicians and sound designers. This is in contrast to Refusion, another approach, which fine-tunes a stable diffusion model. Aha, there you go. On Mel spectrograms, time and frequency, 2D representation of sound, if its stereo is 3D, of music pieces from a paired music text dataset. We use both MuBird and Refusion as baselines for our work, showing that we improve the audio generation quality and adherence to the text description. So there you go, as baselines, something to beat, something to improve upon. Very interesting for us to know. MuBird and Refusion are two other approaches that solve a similar task. Symbolic representation of music, for example MIDI, can also be used to drive the generative process as a form of strong conditioning, as demonstrated by Hang et al. MusicLM enables a more natural, intuitive way of providing a conditioning signal, for example through hummed melody, which can also be combined with a text description. So this is very interesting because you do not need symbolic music. You don't have to write down or use note events that you maybe get from somewhere else. So you just provide the music itself. Looks like to me you just need a single melody and there you go. Another approach, text-conditioned image generation. Precursor to text-conditioned audio synthesis are text-conditioned image generation models, which make significant progress in quality due to architectural improvements and the availability of massive high-quality paired training data. Prominent transformer-based autoregressive approaches present while others present diffusion-based models. The text-to-image approaches have been extended to generating videos from text prompt. Okay, nice to know. Not that relevant for this paper, but also nice to know. The closest to our approach, there you go, among these works is DALL-E 2, OpenAI. In particular, similar to the way DALL-E 2 relies on CLIP for text encoding, We also use a joint music text embedding model for the same purpose. In contrast to DALL-E 2, which uses a diffusion model as decoder, our decoder is based on MusicLM. Furthermore, we also omit the prior model mapping text embeddings to music embeddings, such that the MusicLM-based decoder can be trained on an audio-only dataset, and the music embedding is simply replaced during inference by text embedding. Seems to be a fine trick. So DALL-E, similar approach, different implementation. Joint embedding models for music and text. Mulan is a music text joint embedding model consisting of two embedding towers, one for each modality. The towers map the two modalities to a shared embedding space of 128 dimensions using contrastive learning. Okay, so that's interesting. It looks like to me self-supervised training. The text embedding network is BERT. There you go, good old friend, on a large corpus of text-only data, while we use Retiness 50 variant as an audio tower. Okay, so there's one neural network, BERT, who does the text embedding, and there's another neural network, ResNet 50, which does the audio embedding. Mulan is trained on pairs of music clips and their corresponding text annotations. Importantly, Mulan imposes only weak requirements on its training data quality, learning cross-modal correspondence even when the music text pairs are only weakly associated. The ability to link music to unconstrained natural language descriptions makes it applicable for retrieval or zero-shot music tagging. Retrieval or zero-shot music tagging. In this work, we rely on the pre-trained and frozen model of Huang et al. There you go. So someone already pre-trained such a neural network for us, and in this paper they used that one. Very interesting. Mulan, independent pre-training of models providing the audio and text representations for MusicLM. So we have SoundStream, which I would say, yeah, SoundStream audio to tokens, and then we have BERT, word to vector BERT, Menlos, and we have Mulan here with the two towers, audio, audio, and here we have audio, and we have the text. Interesting, will take some time to digest. Method. In this section, we describe MusicLM and its components. Section 3.1 describes the models that provide the audio representations. Then we show in section 3.2 how we use these representations for text-conditioned music generation. Okay, there comes, well, we would like to know a little bit more about this picture here. First, representation and tokenization of audio and text. We use three models for extracting audio representations that we serve for conditional autoregressive music generation, which are illustrated in Figure 1 on top. In particular, by following the approach of MusicLM, we use the self-supervised audio representation of SoundStream as acoustic tokens to enable high-fidelity synthesis, and W2V BERT as semantic tokens to facilitate long-term coherent generation. More tokens here. For representing the conditioning, we rely on the Mulan music embedding doing training and the Mulan text embedding is at inference time. As well, they are all, I mean, those embeddings are aligned, so you don't need to train on the one. Well, if you train on one, you get the other for free. And all three of these models are pre-trained independently and then frozen. So our feature extractors are pre-trained individually and independently, and then they are frozen, which means that those models are not being fine-tuned during the training of the final model. SoundStream. We use a SoundStream model for 24 kHz monophonic audio with a striding factor of 480, resulting in 50 Hz embeddings. The quantization of these embeddings is learned during training by a RVQ with 12 quantizers, each with a vocabulary size of 1024. This results in a bitrate of 6 kilobits per second where 1 second of audio is represented by 600 tokens. We refer to these as acoustic tokens. This is interesting. So there is some magic at work. What happens here is that 1 second of audio is represented by 600 tokens, which can be quite a lot. I mean, how many seconds do you have in a song? Very interesting. Those are acoustic tokens. They are a lot, but if you remember, when you represent music as time series, you usually have almost 45,000 numbers for 1 second of audio when you go for the pure waveform. Here, having 600 tokens, completely different magnitude. W2BERT. Similarly to AudioML, we use an intermediate layer of the masked language modeling model. Of W2BERT model with 600 million parameters, so a rather big one. After pre-training and freezing the model, we extract embeddings from a 7th layer and quantize them using centroids of a learned k-means over the embeddings. We use 1024 clusters and a sampling rate of 24 Hz, resulting in 25 semantic tokens for every second of audio. Also interesting. So the second pillar, resulting in 25 semantic tokens for every second of audio. So we had acoustic tokens here, and now we have semantic tokens here. Now Mulan. To train MusicLM, we extract the representation of a target audio sequence from the audio embedding network of Mulan. Note that this representation is continuous and could be directly used as a conditioning signal in transformer-based autoregressive models. However, we opt for quantizing the Mulan embeddings in such a way that both the audio and the conditioning signal have a homogeneous representation based on discrete tokens, aiding further research into autoregressively modeling the conditional signal as well. So it's the third pillar, Mulan. Cool. Since Mulan operates on 10-second audio inputs and we need to process longer audio sequences, we calculate the audio embeddings on 10-second windows with 1 second stride and average the resulting embeddings. So you can apply it to longer sequences if you apply it multiple times. We then discretize the resulting embedding by applying RVQ with 12 vector quantizers, each with a vocabulary size of 1024. This process yields 12 Mulan audio encodings, 12 Mulan audio tokens for an audio sequence. During inference, we use conditioning. We use as conditioning the Mulan text embedding extracted from the text prompt and quantize it with the same RVQ as the one used for the audio embeddings to obtain 12 tokens. Conditioning on MA during training has two main advantages. First, it allows us to easily scale our training data since we are not limited by the need of text captions. Second, by exploiting a model like Mulan trained using a contrastive loss, we increase the robustness of noisy text descriptions. Cool. So far, we have 1, 2, 3 different neural networks. They are pre-trained before the actual generative task on some data, giving us different tokens for different representations of our data. And I think, well, this here it comes, hierarchical modeling. That's why we do this, of audio representations. We combine the discrete audio representations presented above with AudioLM to achieve text-conditioned music generation. For this, we propose a hierarchical sequence-to-sequence modeling task where each stage is modeled autoregressively by a separate decoder-only transformer. Haha, there you go. So we have multiple stages, and each stage is a decoder-only transformer, which means GPT. Here we go again. The first stage is a semantic modeling stage, which learns the mapping from Mulan audio tokens, so these ones, to the semantic tokens S by modeling a distribution where T is the position in the sequence corresponding to the time step. The second stage is acoustic modeling stage, where the acoustic tokens are predicted conditioned on both Mulan audio tokens and the semantic tokens, modeling the distribution. So taking into account the bird model here as well. The second stage is the acoustic modeling. The first stage is the semantic modeling. Notably, to avoid long token sequences, it's always a bottleneck. So maybe you only have 1024, 2048, or 4096, or maybe more tokens that you can model at the same time. MusicLM proposes to further split the acoustic modeling stage into a coarse and a fine modeling stage. So the acoustics gets split into fine and coarse. We rely on the same approach where the coarse stage models the first 4 levels from the output of a sound stream RVQ, and the fine stage models the remaining 8. So they refer to something else to have a look at. Cool, 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 cool. The plot thickens, here comes a good part. Experimental setup. Models. We use decoder-only transformers. Again, GPT. Like. For modeling the semantic stage and the acoustic stage of MusicLM. The models share the same architecture, composed of 24 layers, 16 attention heads, an embedding dimension of 1024, feed-forward layers of dimensionality 4096, dropout of 01, and relative positional embeddings resulting in 430 million parameters per stage. So 3 stages, all 24 decoders, 16 attention heads, so multiple information flows per decoder at the same time. Embedding dimension, we are all working, mixing embeddings or token sequences. Feed-forward layer, there's an output and inward projection in the feed-forward, in the decoders dropout, regularizing, and relative position embeddings, so that we know, or the transformer knows, where we currently are in the sequence. Cool. By relying on pre-trained and frozen Mulan, so this model is pre-trained and frozen. Pre-trained we already saw, and frozen is we don't change the trainable weights and parameters, weights and biases, the trainable parameters with stochastic gradient descent. We need audio-only data for training the other components of MusicLM. We train SoundStream and W2Bird on the free music archive dataset. Now, this is interesting. Another dataset training those other models, whereas the tokenizers and the autoregressive models for the semantic and acoustic modeling stages are trained on a dataset containing 5 million audio clips. 280,000 hours of music is 24 kilohertz. This is very, very strong. So it seems to me that pre-training those feature extractors already takes quite a lot of effort and energy. Each of the stages is trained with multiple passes over the training data, multiple epochs. Sometimes when you take a look at models like GPT-2 and GPT-3, you realize that they usually train it only for one epoch. We use 30 and 10-second random crops of a target audio for the semantic stage and the acoustic stage respectively. The MusicLM fine acoustic modeling stage is trained on 3-second crops. So there we are, still training the feature extractors. During inference, we make use of a joint embedding space between audio and text learned by Mulan. So via contrastive learning, they are all close to each other in embedding space, text and audio. That is, we substitute MA with MT, which you can do. So suddenly you have text conditioning. We then follow the stages described above and obtain A given MT. We use temperature sampling for the autoregressive sampling. So, okay, there is some randomness when predicting the next token. With temperature 1 for the semantic modeling stage, 0, 95, and 0.4 for the coarse and fine acoustic modeling stages, respectively. These temperature values were chosen based on subjective inspection to provide a good trade-off between diversity and temporal consistency of generated music. So there you go. Temperature, as always, you have to find a good value yourself. Now, evaluation dataset. To evaluate MusicLM, we prepare MusicCaps, a high-quality music caption dataset which we make publicly available. So yet another dataset. I think I should create a list of datasets that are involved. This dataset includes 5,500 music clips from audio set. Each paired with corresponding text descriptions in English, written by 10 professional musicians. For each 10-second music clip, MusicCaps provides a free text captioning consisting of 4 sentences on average, describing the music, and 2, a list of music aspects describing genre, mood, tempo, singer voices, instrumentation, dissonances, rhythm, etc. So there you go. Describing the music aspects as part of a dataset. Very interesting to say the least. On average, the dataset includes 11 aspects per clip. See Appendix A for a few captions. Okay, there seem to be examples. I'm always curious about the appendix because sometimes the authors hide a lot of very fruitful details in there. MusicCaps complements AudioCaps as they both contain audio clips from audio set with corresponding textual descriptions. However, while AudioCaps contains non-music content, MusicCaps focuses exclusively on music and includes highly detailed expert-provided annotations. Always good, high-quality annotations. The examples are extracted from both the train and eval split of audio set, covering a diverse distribution of genres, as detailed in, again, Appendix A. MusicCaps also provides a genre-balanced split of data with 1,000 examples. Metrics. We compute different metrics to evaluate MusicLM, capturing 2 important aspects of music generation, the audio quality and the adherence to a textual description. That's quite interesting. How are they going to check that? There's a freshet audio distance, FAD. The freshet audio distance is a reference-free audio quality metric which correlates well with human perception. Models producing samples with low FAD score are expected to generate plausible audio. However, the generated samples might not necessarily adhere to the text descriptions providing conditioning. So this is how it sounds like. Does it sound good? Does it sound bad? We report the FAD based on 2 audio embedding models, both of which are publicly available. Trill, which is trained on speech data, and VGG-ish, which is trained on YouTube 8 million audio event dataset. So we have already left the generative phase of this whole paper. Now it's about evaluating. So there's one number that we now have, FAD. There comes the other, the KL divergence. There is a many-to-many relationship between text descriptions and music clips compatible with them. It is therefore not possible to directly compare the generated music with the reference at the level of the audio waveform. To assess the adherence to the input text description, we adopt a proxy method similar to the one proposed by, specifically we use a LEAF classifier trained for multi-label classification on audio set to compute class predictions for both the generated and the reference music and measure the KL divergence between probability distributions of class predictions. Okay, so you take the samples, you map them to probability distributions using dimensioned approaches, and in order to find the distance between probability distributions, you use the KL, Kuller-Leibeck divergence. When the KL divergence is low, the generated music is expected to have similar acoustic characteristics as the referenced music, according to the classifier. Then they have another measure. So there's one here, one before was FAD. Now comes the Moulin cycle consistency. And the Moulin cycle consistency, MCC, as a joint music text embedding model, Moulin can be used to quantify the similarity between music text pairs. Quantify the similarity between music text pairs. It's contrastive learning, so it maps into some geometric space. We compute the Moulin embeddings from the text descriptions in MusicCaps, as well as the generated music based on them, and define the MCC metric as the average cosine similarity between these embeddings. There you go. Use Moulin to embed everything into latent space. Latent space is so geometric that you can use the cosine similarity in order to measure semantic similarity. Qualitative evaluation is another number. Ultimately, we rely on subjective tests. is where it gives me lots of smiles, because always you have to listen to it. You have to ask people how they like it. There's not one big objective number or objective measure where you just feed in your music and tells you how good it is. No, you always have to show it to people. The adherence of generated samples to the text description. We set up A versus B human rating task, in which raters are presented with a text description and 2 samples. Okay, that's cool. So we play a game with different samples. You get a text description and 2 samples, which one is closer. And if you do it multiple times, you get a rank order of the samples. Or one model and a reference music. Okay. There are 5 possible answers: strong and weak preference for A and B, or no preference. The raters are instructed not to take the music quality into account when making the decision, because this is aspect of the evaluation is already covered by the FAD metric. This is interesting, which might be a little troublesome or stressful for people who actually do the evaluation, that don't be fooled by the quality, how it sounds like different measure. We consider the output, little math, to aggregate the results of pairwise. We count the number of wins. That is how often a condition is strongly or weakly preferred. The samples are selected from a genre-based 1K subset of our evaluation data. So that's the game that they play. Sounds a little like to me how you do rankings of players in chess and Go. And then finally, I think this last one, training data memorization. How much of the training data is actually memorized? So when the neural network generates something, how high is the chance that this is just a copy from the training data? Large language models have the capacity to memorize patterns seen in the training data. Fine. We adapt the methodology used in Kalini et al. To study the extent to which MusicLM might memorize music segments. We focus on the first stage responsible for semantic modeling. We select n examples at random from the training set. For each example, we feed the model a prompt which includes the Mulan audio tokens, followed by a sequence of the first T semantic tokens S, corresponding up to 10 seconds. So they take some sample from the dataset, they use a part of it, not the entire part. We use greedy decoding to generate a continuation of 125 semantic tokens, 5 seconds, and we compare the generated tokens to the target tokens of the dataset. Very important, greedy decoding means no randomness. Temperature is 0 or not used at all. So this is where the decoders, the transformers, are very, very deterministic. No randomness. We measure exact matches as the fraction of examples, which you can do, for which generated and target tokens are identical over the whole sample segment. So you generate something and then you find out how many things are copied. In addition, we propose a methodology to detect approximate matches based on the observation that sequences of seemingly different tokens might lead to acoustically similar audio segments. Aha, there you go. Ambiguity in the data. Different representations, similar sounds. Namely, we compute the histogram of semantic tokens counts over the corresponding vocabulary from both the generated and target tokens and define a matching cost measure between histograms and follows. So we do token counting, and once we hit a threshold, then it qualifies as a match. First, we compute the distance matrix between pairs of semantic tokens, which is populated by the Euclidean distances between the corresponding k-means centroids used to quantize W to V buried to semantic tokens. Then we solve an optimal transport problem to find the matching cost between a pair of histograms using the Sinkhorn algorithm, considering only the submatrix corresponding to non-zero token counts in the 2 histograms. To calibrate the threshold used to determine whether 2 sequences might be approximate matches, we construct negative pairs by permuting the examples with target tokens and measure the empirical distribution of matching costs for such negative pairs. We set the match threshold to 0.85, which leads to less than 0.0% false positive approximate matches. So it's quite a huge cup of tea, but it tells us here they have a methodology with multiple metrics, how to find out the quality of the generated artifacts amongst different dimensions, even including a human evaluation, which is quite cool. So most of the stuff can be computed with some human tuning, but most most of the stuff is I would say, automatic. Results. We evaluate MusicLM by comparing it with two recent baselines for music generation from descriptive text, namely MuBird and Refusion. That's what they've promised at the beginning. In particular, we generate audio by querying the MuBird API and by running inference on the Refusion model. We perform our evaluations on MusicCaps, the evaluation dataset we publicly released together with this paper. Cool. Comparison baselines. So I think here is where it gets interesting. Comparison to baselines. Table 1 reports the main quantitative and qualitative results of this paper. In terms of audio quality, as captured by the FAD metrics and FAD-FGG, MusicLM achieves better scores than MuBird and Refusion. Here's the winner. Here's another winner. It's rather small. On FAD Trill, MusicLM scores similar to MuBird. Okay, there you go. That number here. MusicLM is capable of generating high-quality music comparable to MuBird. Quality compared to MuBird, which relies on pre-recorded sounds prepared by musicians and sound designers. In terms of faithfulness to the input text description, as captured by KLD and MCC, MusicLM achieves the best scores. So here, best scores, MusicLM here, and there, smaller here, bigger there. In order to faithfulness to the input text description, as captured by KLD and MCC, MusicLM achieves the best scores. Oh, Jesus Christ, is very good, because then, well, you do not have to do this subjectively. We further supplement our evaluation of text faithfulness with human listening tests. That's fine, always good, as long as you don't do it all the time. Participants are presented with two 10-second clips and a text description, as we already discussed. Like a scale, we collect 1,200 ratings, with each source involved in 600 pairwise comparisons. So it might be a little bit expensive if you have to ask people for so many ratings. Table 1 reports the total number of wins, that is counting how often the human raters preferred a model in a side-by-side comparison. MusicLM is clearly preferred over both baselines. There you go. Here's the number, significantly higher. Listening to examples in which the ground truth was preferred over MusicLM released the following patterns. Captions are extremely detailed, referring to more than 5 instruments or describing non-music aspects as wind, people talking. Captions describe temporal ordering of the audio being played. Negations are used, which are not well captured by Mulan. Overall, here comes it. Here comes the good part. We conclude that our approach is able to capture fine-grained information from rich free text captions of MusicCaps. The KLD and MCC metrics provide a quantitative measure of the faithfulness of a text description, which is in accordance with the human rating study. There you go. And then they dig a little bit deeper. Importance of semantic tokens. To understand the usefulness of decoupling semantic modeling from acoustic modeling, we train a transformer model which directly predicts coarse acoustic tokens, so yet another model. By modeling this distribution here, we observe that while the FAD metrics are comparable, KLD and MCC scores worsen when removing the semantic modeling stage. So you see, you need the semantic modeling stage to get high quality. In particular, the KLD scores increases from 1.01 to 1.0.5, and the MCC score decreases from 0.51 to 0.49, indicating the semantic tokens facilitate the adherence to the text description. There you go, it's the semantic tokens that do that. We also confirm this qualitatively by listening to the samples. In addition, we observe degradation in long-term structure. There you go. You cannot just plug out one of those pillars from the final models. Information represented by audio tokens. We conduct additional experiments to study the information captured the semantic and acoustic tokens. In the first study, we fixed the Mulan text tokens as well as the semantic tokens. So many studies that they did. They differ in terms of we provide samples from this. Okay, and there's how much information is represented by the audio tokens, and the memorization analysis says Figure 3 reports both exact and approximate matches when the length of a semantic token prompt is varied between 0 and 10 seconds. we observe that the fraction of exact matches always remains very small. There you go. 0.2% copies, even when using a 10-second prompt and generate a continuation of 5 seconds. Novelty. Figure 3 also includes the results for approximate matches. We can see a high number of matches detected with this methodology, also when using only Mulan tokens as input. We include a sample of approximate matches obtained with temperature 0 in the accompanying material. Note that the acoustic modeling carried out by the second stage introduced further diversity. Cool. And generated samples also when the semantic tokens match. Exactly. Extensions. So putting things on top of it. Not only they have very, very interesting pre-training plus generative task modeling and some evaluation, they also have extensions on top of that. Melody conditioning. We extend MusicLM in such a way that it can generate music based on both a text description and a melody, which is provided in the form of humming, singing, whistling, or playing an instrument. Okay, this is cool. This requires extending the conditioning signal in a way that captures the target melody. To this end, we create a synthetic dataset composed of audio pairs with matching melodies but different acoustics. To create such pairs, we use different versions of the same music clip, such as covers, instrumentals, or vocals. Additionally, we acquire data pairs of people humming and singing. We then train a joint embedding model such that when two audio clips contain the same melody, the corresponding embeddings are close to each other. For implementation details, we refer to Appendix C. So there's another paper hidden inside that paper. To extract the melody conditioning from USML, we quantize the melody embeddings with RVQ, as before, and concatenate the resulting token sequences with the Mulan audio tokens. So there's those tokens and the Mulan tokens. During inference, we compute melody tokens from the input audio clip and concatenate them with the Mulan text tokens MT. Based on this conditioning, MusicLM can successfully generate music which follows the melody contained in the input audio clip, while adhering to the textual description. So we have a melody, and based on some text, you create some audio out of it. Long generation in story mode. In MusicLM, generation is autoregressive in the temporal dimension, which makes it possible to generate sequences longer than those used during training. In practice, the semantic modeling stage is trained on sequences of 30 seconds. To generate longer sequences, we advance the stride of 15 seconds, using 15 seconds as prefix to generate additional 15 seconds, always conditioning on the same text descriptions. So you have something like a moving window through time where you always take into account 15 seconds and predict the next 15 seconds. Of course, you lose something at the beginning, but this is rather natural. And I have to tell you, I use this in my work as well. With a small modification, we can generate long audio sequences while changing the text description over time. Borrowing from, in the context of video generation, we refer to this approach as story mode. Concretely, we compute MT from multiple text descriptions and change the conditioning signal every 15 seconds. So you have a story that you tell with a couple of words, a couple of sentences, and you move through the sentences. The model generates smooth transitions which are tempo consistent and semantically plausible, while changing music context according to the text description. This is really, really cool. Conclusions. We introduce MusicLM, a text-conditioned generative model that produces high-quality music at 24 kHz, consisting over several minutes, while being faithful to the text conditioning goal. We demonstrate that our method outperforms baselines in music apps, a hand-curated, high-quality dataset of 5.5K music text pairs prepared by musicians. Cool, beating the baseline, high-quality music, highly consistent. Some limitations of our method are inherited from Mulan, in that our model misunderstands negations and does not adhere to precise temporal ordering described in the text. That's fine, okay. Moreover, further improvements of our quantitative evaluations are needed. Specifically, since MCC also relies on Mulan, the MCC scores are favorable to our method. Future work comes a crucial part. Future work may focus on lyrics generation, along with improvements of text conditioning and local quality and vocal quality. Another aspect is the modeling of high-quality, high-level song structure like introduction, verse, and chorus. That they don't have yet. So that, well, although you have something like a story mode, you don't get a story told in combinations of verse, chorus, bridge, intro, and outro. Modeling the music at a high sample rate is an additional goal. Well, if you have super sampling, then maybe you don't need that. Broader impact. MusicLM generates high-quality music based on a text description, and thus it further extends the set of tools that assist humans with creating music tasks. It's always good. More tools for creative humans, not replacing the humans. However, there are several risks associated with our model and the use case it tackles. The generated samples will reflect the biases. Of course, there's biases present in the training data. If you train on Rammstein only, you will not get classical music. The generated samples will reflect the biases present in the training data, raising the question about appropriateness of music generation for cultures underrepresented in the training data. Very important point. While at the same time also raising concerns about cultural appropriation. Debatable. We acknowledge the risk of potential misappropriation of creative content associated with the use case. In accordance with responsible model development practices, we conduct a thorough study of memorization, adapting and extending a methodology used in the context of text-based LLMs. Memorization, copyright infringement. Focusing on the semantic modeling stage, we found that only a tiny fraction of examples was memorized exactly, while for 1% of examples, we could identify an approximate match. We strongly emphasize the need for more future work in tackling these risks associated with music generation. We have no plans to release the models at this point. What? No plans to release the models at this point? Is this really the last sentence? Really the last? It is the last sentence. Now, after all this excitement, going through this paper, trying to find out what this paper is about, we say it in the last sentence: we have no plans to release models at this point. Well, no way to do more with that. So the final disappointment stands. There's no plans to release the models at this point. Well, cool. Okay. Well, thank you very much for being part of this race through a paper that I was always curious about for a couple of weeks now. I hope you were at least a little bit entertained about my approach, how to try to get as much as possible out of this paper. I think it has been a couple of minutes. If you like this, please provide some feedback. Well, I got some feedback on me reading a previous paper, which was really gorgeous, and people like that. So if you'd like to keep me going, please subscribe to this channel. Also, if you have some questions or some comments, please write something in the comment sections. Have a nice day.